The wire ducting we've selected is about 40 millimeters wide by about 60 millimeters tall. So given that, we're going to mount the wire duct on the center line of about 3/4 of an inch. That'll give us a small amount of relief around the edge. So we're going to go ahead and mark that off using a dry erase pen directly onto the back plate. Okay, quick check-in. I've cut all the wire duct and laid it out and then placed the components in between to just get a test fit to see how everything is going to work. I mentioned earlier a quick tip when laying out panels to use a dry erase pen. And this allows you to make marks right on the back panel and then erase them with your finger. I also use just some standard tin snips to trim the wire duct in between the finger notches. So what we see here is on the bottom, high voltage devices. In the middle will be terminal blocks, and the top will be the low voltage devices, including the UniShield. We'll likely have to move the power supply to that top location, but we'll still have plenty of room for the other devices there. So now I'm going to drill the holes for the wire duct, lay out the DIN rail, and get it all mounted. I have drilled and deburred all of the holes for the wire duct, and I'm going to go ahead and mount those up now. Then we'll measure and mark the DIN rail and cut and mount those as well. And now you can see all of the wire duct is installed. Now we will measure and cut and mount the DIN rail. Here's the finished panel with DIN rail mounted. You can see we riveted everything in place. I like rivets for this application because they don't come loose. There's nothing to be left rattling around in an electrical box. They're quick, easy, and permanent, and they have a flush head so that nothing interferes or any wires get snagged. Now you'll notice these DIN rails are in the center of their respective wire ducts, but this one where the high voltage rail is not. And there's a reason for that that I'll show you in a few minutes. Okay, now all of the components are back on the panel mounted on the DIN rail. Let's take a walk through what we have again. So we have our high voltage rail at the bottom, contactors, circuit breakers, fuses. We have the 2-element SSRs. These are SSR modules with integrated heat sinks. As I mentioned earlier, this is going to save us from having to put a big hole in the box and mount an external heat sink. And because the box is so large, it will be able to sink the heat of those SSRs. Each of these SSRs tends to dissipate about 30 to 40 watts. So at most that's 80 or 100 watts of heat. Shouldn't be too much of a problem in such a large metallic box. The accessory SSR bank is mounted here. And then as we go to the terminal block rail, we have terminal blocks for ground, neutral, and our legs. In fact, I'm missing 4 terminal blocks. I need to add those. So that'll be ground, neutral, leg 1, and leg 2. And then we have terminal blocks for our low voltage, so there'll be ground, 5 volts, and 24 volts. And this will make wiring quite a bit easier. Then on the top rail, we have our 24 volt and 5 volt power supply. The 5 volt power supply is that DC to DC unit mounted next to the 24 volt power supply. And then, I didn't show this earlier, but we have 3 DIN rail carriers. This will be the analog amplifier, this will be the UniShield, and this will be the RTD platform. So the general design of this board keeps all the low voltage up in this quadrant and all the high voltage down in this quadrant. That should help mitigate any noise issues that might pop up. Now I mentioned earlier there was a reason why the high voltage DIN rail was not centrally located between the wire duct, and I'm going to show you that reason now. This contactor is our main contactor, and it will have 6 gauge wire feeding it. In fact, that wire will come in through the side of the box, go through this wire duct, make a turn, and then come into the contactor. And the challenge is, when you think about it, it's got to go from this contactor into this circuit breaker bank per the schematic. Now, that would require breaking this 6-gauge wire out into respective additional 6-gauge wire terminal blocks and then split into the 3 breakers. And because the breaker is downstream of the contactor, we'll have to maintain 6-gauge wire all the way. So to add those terminal blocks means additional space, additional wires, additional points of failure. And the way to bypass that or make things easier is a bus bar. A bus bar looks like this. It's got 3 parallel sets of legs, and the bus bar installs into the breakers this way to jump them together. But now you might ask, well, how do I get the power from the contactor into the bus bar? And for that, we'll use a single terminal lug. Here's a look at the terminal lugs installed together. And now you can see why we shifted the high voltage rail a little bit lower in between the wire duct to accommodate that single terminal lug. And these lugs look like this. And you can see how it sits underneath the bus bar and that tab meets together inside the breaker. So now we just need to come out with a single 6-gauge wire from the contactor into the bus bar, and then all of our power is correctly distributed into the circuit breakers, and then we go with individual circuits out to our contactors. Just a little tip, make things easier. Okay, that all said, that will be it for the second video in this build series. We're going to move on to the box and start to drill holes in the side to accommodate all of our devices. We're going to use a drawing for that. We'll see you in the next video.